Hey everyone, today I wanted to go and sort of do a part one for hopefully a two-part series on zeta function or Riemann zeta function when s equals 3. So I have it written out here. We have zeta of s is, oh I forgot the equal sign, equals the sum as n goes from 1 to infinity of 1 over n to the s, and s equals 3 in this case. So it's 1 over n cubed as n goes from 1 to infinity. Now we don't know what the sum equals, that's what we're trying to find, and I wanted to compare to the Basel problem, where zeta function when s equals 2, so that's the sum as n goes from 1 to infinity of 1 over n squared, and we know that this equals pi squared over 6. So, which is approximately equal to like 1.6 something. Hold on. Let me find what it's actually equal to. Pi squared over 6 is something. I don't have it written down. Just kidding, yes I do. It is approximately equal to 1.6449. I could have just done that on a calculator. So that's like a rough decimal approximation of the whole, what do you call it, the Basel problem. And what we do know is that what we're trying to find, zeta of s when s is equal to 3, is that zeta of s when s equals 3, I'll just say 1 over n cubed, has to be less than 1 over n squared, because cubing something makes a number larger than squaring something, and if we're dividing by a larger number, we would ultimately get smaller and smaller decimals. So we know that, here I'll write it, like, where is my, alright, I'll write it here. We'll say 1 over n cubed is less than 1 over n squared, and we know this. I'll just say we know this. So now, what we're essentially trying to find is how much less, and that's going to be the crux of what I do. So the first thing I want to do is write out a couple terms of 1 over n cubed. So we would have, why does my cursor, oh here it is. Okay, so we would have, I'm gonna skip one because that's like trivial. So we'll have 1 over 8, because 2 cubed is 8, and then 1 over 27 plus 1 over 64 plus 1, that's a crappy plus sign, 1 over 125, and so on and so forth. Now I want to write some terms of the Basel problem in terms of cubing it, so giving it a common denominator for each term. So instead of having the usual, 1 over 4 plus 1 over, what is it? 1 over 4 plus 1 over 9 plus 1 over 16. Instead of having just that, I'll write those out too. 1 over 4 plus, and I'm skipping 1 this time too, because those, you'll see why in a little bit with what I'm trying to do. Oops. 1 over 16 plus 1 over 25. Rather than having it be like this, I want common denominator for each one, so that what we're trying to find is the difference between the two. And so by finding the difference, we can just take that difference, subtract it from what we do know, which is pi squared over 6, and get what zeta when s is equal to 3 should equal. So that's sort of like the whole goal I have here. So we have 1 over 4 plus 1 over 9 plus 1 over 16 plus 1 over 25, and I want to write it in terms of the 1 over n cubed. So we want to essentially multiply or make all these the same common denominator as the ones above. So we would have 2 over 8, because 1/4 is equivalent to 2 over 8, plus 3 over 27, plus 4 over 64, plus 5 over 125. Now, if we were to subtract these from the the values above, 1 over 8 plus 1 over 27 plus 1 over 64 plus 1 over 125, what we would get. So here, I'll make an arrow. We'll just do the minus sign. So we're subtracting here. This difference ultimately gets us negative, and they're all negative, and we want that, and I'll explain in a little bit. So we get negative 1 over 8 plus negative 2 over, I'm not going to have enough space. I'll keep writing anyway, it doesn't matter. 3 over 64 plus negative 4 over 125. So this is just the difference of some of the first few terms of 1 over n squared and 1 over n cubed. And so there's already a sort of a clear pattern emerging from this. And so I want to essentially generalize a formula so that I can not only find the difference of any given term, say, oh, if we had n equal 100 for each respective function, what would their difference be? I'd not only be able to generalize a way to find any term, but also sum up the difference of each individual term so that I could have the total difference and subtract that from pi squared over 6 to get what 1 over n cubed is equal to. So that's sort of the gist of what I'm trying to do. So after we found this little pattern, we noticed that these, when when subtracted, well, you see it's 1, 2, 34, obviously, and they're all negative because we know that, like I said earlier, 1 over n cubed is less than 1 over n squared. So when we add this difference, it'll be a negative number, which would subtract from pi squared over 6. We don't want it to be larger. That wouldn't make any sense. So given this apparent relation between each one, the formula that I want to sort of come up with here, I need more space. Here, what do I want to erase? Alright, I'll erase like all of this. So I'll also erase this arrow, and this line, and this dot. Okay. So given these couple of terms here that we sort of know, we can generalize the formula of negative. Hold on, let me rewrite that. We'll have n minus 1 over n cubed. This whole thing is negative because we want the ultimate difference to be a negative number. The way I got this is, what you'll notice is, well, I guess I erased it, but we had, was it 4 over 64 when compared to 1 over 64 of 1 over n cubed. We had 2 over 8 versus 1 over 8, 3 over 27 versus 1 over 27. So everyone at the top is 1. Every numerator for n cubed, 1 over n cubed is 1, obviously, because that's the function. But when we convert 1 over n squared to have a common denominator with all the ones at the top, you notice that when subtracting 1, we get this equation, n minus 1 over n cubed. So in order to, I guess, test to make sure this generalized formula works, I'm gonna plug in some terms. So let's say we want 7, right? 7 minus 1 is 6, and 7 cubed is 343. So we have negative 343. So that's n equals 7. So that spits out negative 6 over 343. And of course we could check that. So for 1 over n cubed, we would have 1 over 343, because 7 cubed is 343. And for 1 over n squared, well, 7 squared is 49. So we'd have 1 over 49. We want to get the common denominator of 343. So we multiply by 7, we get 7 over 343. So if we do 1 over 343 minus 7 over 343, that gets you negative 6 over 343, which is what we got here. So we know that at the very least, this generalized formula can find the difference of any two terms for 1 over n cubed and 1 over n squared when we subtract them. So now that we know that this formula here actually works, we want to find the actual difference. We want to, not the difference of just any individual term, but rather the sum of all the differences, which is exactly what we're going to do. So in order to do that, we would write the new sum. So we would have the sum, that's a crappy sum sign, but whatever, as n goes from 1 to infinity of negative parentheses n minus 1 over n cubed. So what this does with this generalized formula is essentially say, okay, given any n, I could not only find the difference between 1 over n cubed and 1 over n squared, but using, a sum, we can sum up all the differences, and then from there we would add that difference to pi squared over 6 and find what 1 over n cubed actually equals. Unfortunately, I do not know the answer to this. Well, I know the answer, but I wouldn't know a way to get to the answer without just doing some really boring number crunching. Of course, you could write out, like, a lot of terms. You could go to, like, the 100th term or some arbitrary value where n minus 1 over n cubed is so infinitesimally small that it has almost no effect on the sum. You cut it off there, say that's your limit, and then we'll add up all the numbers we do know with a calculator or whatever, and we would find the answer. But that's no fun, and I want to find a way to do it out on hand, which is why there's going to be a part 2 to this, because I'm not smart enough to know, what the answer to the sum is. But for now, we do know that this is in fact it's the formula that we want. It's the equation, the sum that we want, that not only generalizes and allows us to find the difference of each individual term of the two respective functions, but also allows us, when used with summations, to find the sum of all those differences and eventually get what zeta of 3 is equal to. So I guess our penultimate goal, and I'll write this for part 2 here. Let me move this here. We'll cover that up here. We'll leave that there. So ultimately, what we're trying to find, or our ultimate goal is, we would take the sum and goes from 1 to infinity of 1 over n squared, and we would subtract, or rather I guess add, because this will be negative, the sum as n goes from 1 to infinity of negative n minus 1 over n cubed. And this should equal our sum as n goes from 1 to infinity of 1 over n cubed. So by finding, well, we know what 1 over n squared is, that's pi squared over 6, but finding the sum of the differences of each individual term for 1 over n squared and 1 over n cubed, and subtracting that from 1 over n squared, we should be able to arrive at the result that'll tell us, at least if not exactly, a good rough approximation for what 1 over n cubed is, if I decide that it's too hard and I don't want to write out all the terms. So yeah, pretty unsatisfying result. I don't have an answer, and this video was super unstructured, and I don't really know what I'm talking about, but this is where we're at now, and hopefully I'll have a part 2 when I actually, hopefully, figure out how to figure out the sum, and then give at least a decent answer to what zeta of 3 is. Yeah. Thank you for watching, and come back for part 2 whenever I figure out what the sum is.